bring my assumption X, A in here. Okay, so implications are right associative. Okay, so I have here B implies C, and then I do another implication introduction rule, and I get to the point where I have X A, Y A, where I have this C, and I have that. And all that happens now in the contextual type. You might say, well, all that happens is that I do one step. I go from the type XA, YB, C, directly to this type, proof C, in the set of assumption, XA and Y. Yes?
Shouldn't Y be set to be on the top on the left?
Huh? Oh, yeah, it should be Y. This one here? No, it should definitely be Y.
Top left.
Top left.
The type of Y.
Ah, it should be a B. Very good. Thank you. Somebody's alive. Okay, very good. Okay, so this is sort of like almost looks like a shortcut than what we could be doing here. And indeed, okay, we can actually write a transformation that will translate proof of this form into this form and vice versa. Okay, these are theorems. Okay. And these theorems are called sometimes lowering and raising, and we can define them, or we can define the transformation for these types if you want to. But what will be different is the kind of program we will actually have when we use these assumptions. So let's look at two kinds of, at an example, okay, how the program will change. And the example I want to give is essentially a very simple one. Going to be, I want to prove C implies A, implies box C implies D, implies A. So how are we going to prove this? What's the proof term for this? Maybe we can just write the proof term rather than the whole derivation. See whose brain is still alive at 4:26.
It's named the proof term, right?
The proof term. Yeah, so it must be a lambda. Okay.
Lambda.
Lambda. Okay, good. So it must be a lambda. And I do the easy part. Okay, this is going to be of type C implies A. And then we need to create a box.
In the box of
Lambda,
Well, we want to
Y,
not
Z.
create the box right away because we want to still, have access to C implies A.
Oh yeah.
Oh yeah, right. So we want to move that to our forever context. So we're going to do a let box. Okay, and this will now mean we have here in delta we have some assumption U that will say C implies A is valid. And now we want to create a box. Okay. And what is that box going to be?
Lambda,
It's
Y.
going to be another lambda. Okay. Not good at using my board today. Okay. Be a bit more economic here. Box. Okay. So we'll have a lambda. Okay.
Y.
Y.
Not lambda Z.
So it will be of type Z. That will be
Z.
Z. Then it will be a E.
UY.
U applied to Y. Okay, so the thing I want to point out, maybe I'll put that on the next slide here, so we can see this better. Box. Okay. All right, so we see that we have here a number of abstractions. And we're using the U as part of an application. Okay. All right, so out of the proof change, if I have, if I want to construct something of the form box, X, A, S, okay. And I'm going to say that this implies the box, okay, where I have Y, it's going to be a C, and I say D, and under this context I have to construct something of type. So it'll be still a function, right? We're going to still start with a function, let's say X. It currently takes in this, so maybe I shouldn't call this X, X prime, which will take in a C and an A. Okay, so then we still do a let. Of the X. Okay. The U will be open, will be standing for something that waits for some X prime. Okay. And now we're going to build our box. Okay, and the box is open, it will contain C and Z, E. And what will happen here in the body? We want to use U. Okay, so we're going to use a closure of U. And what's the substitution we need to do? How can we use U? So U will be this thing. Okay, that's what U. U stands for something that will produce an A, which is the thing we need, but it might use some different variable. It might use X prime. Yeah.
Are we turning Y into X prime somehow?
Exactly. We're going to turn these X primes into Y's, okay? Because they have the same type. And so we are associating this with the substitution that basically says use Y for this X prime. Just a one mapping because we only have one variable in U, so we only need to map the X prime into that. So the difference here is that here we have an application, possibly a regex that will remain in the box because we don't evaluate under the box. Here we have closures, and closures fire. Okay? They fire as soon as I know what U stands for. So the computational behavior will be different. So that means it's not the case that we can prove more things in contextual type theory. We can prove the same kinds of propositions as we were able to prove before. So from a proof theory point of view, it's not interesting. There's nothing we gain in proving. What we gain is a difference in what these programs will look like. So here we're creating functions, here we're creating applications, so we might create redices, here we will not have redices. Yeah?
So to connect this back to the macro perspective, you wrote closure to mean like application of this code fragment, but does that actually have to create a closure at runtime if you were to implement this?
So in this case here, it doesn't really, okay, because this was a simple renaming, okay, and that is essentially a beaconing substitution. So You can think of this as omitting it. I'm not writing it. But in general, right, we can actually create interesting instantiations. So I want to revisit the nth program we've seen yesterday. And I'm going to revisit the power function. And these are really two examples of how we can use it for metaprogramming. Okay? And we'll see how the programs will differ this time around. Okay, so that's the goal. So let's do the nth function. So nth will now say I'm going to take an integer or a natural number, okay? And I'm going to create a code fragment that is waiting for the vector. Okay. And then it is returning a bool. That's the type of the nth function. And nth of 0 will create something like a box. And where v is still the spool vector. And it will return the head of v. And then of successor of n will make a recursive call to n of n. And then we'll rebuild something. Okay, we'll rebuild e, which is a bool vector. And we're going to, what did we do? We used this guy, and what did we do with it in order to get like the next element in our list? The tail, okay. That we applied it, like previously it was a function, and we applied it to the tail of v, okay. Now we're not applying it to the tail of v. We're going to just really plug in for whatever the vector was previously here. We're going to plug in tail of v. Okay. So we're going to say in the closure of u, where we plug in the tail of v, okay, for what, let's say, of v0, like from the previous stage. Okay. So often we don't write the domain here because this v0 seems to be completely unbound. Okay. And it's unnecessary because we know exactly what the type of u is. It's going to be have one element. Okay. So, but if you want to think of this, it is really a renaming. So what will happen? Okay, so let's see. N of 2. Okay. Hopefully I'm not so ambitious. Okay, so that means we need to compute net box u of n of 1. Okay. In box of the bool vector. Okay. And here we have a closure of u, tail of. So what's n of 1? Well, that's going to generate something like box u, n of 0. A box E, which is a Boolean vector of the closure of your tail of V, okay. Essentially for V0, if you want to say something like that. Okay, so this up here would be tail of V for V1. Like the vector we had. Tail of V, let's say for V1, like from this previous stage. So this is like morally like has here V1. what's nth of 0? Nth of 0 is going to be some box, okay, which has this B0. I'm going to not write the type because otherwise I'm going to run out of space, but it's going to be head of B0. And I want to use that in the body. So let me allow you to drop this type. Okay. So this will be essentially a closure of U and the tail of V or B0. So now we bind U to this expression. Yeah. And we're going to find the instantiation of U, which is this one. And we need to evaluate the closure of a concrete term, okay, in the head of E0, together with this mapping of tail of V or E0. And that closure, that is not syntax in our language, because in our language we only have closures of variables with mappings. Okay. And that means we will actually evaluate here at this point. Okay, so this isn't something we will create, but rather we will actually evaluate to a term that will say box of V. And what does it mean if I replace V0 with tail of V? I will get head of tail of V. So this is going to be my actual result. Because this is going to be eagerly eliminated, this closure. Yeah?
And it's eager because the substitutions they have a certain status.
That's right, yeah. So the substitution, here we cannot apply them, right, in this closure. We don't know what U stands for. So they must be suspended. I must have a proper closure. But as soon as I know what U stands for, okay, as soon as I have a term, I can actually apply it. Okay, I don't have to keep that closure. I can actually apply it. Yeah?
Is that somehow like in the logic, or is it?
That is in the logic, that's right. So the way we define, in fact, substitution for these modal variables or valid variables U, right? So we saw that we have two different kinds of substitution operations. We saw that yesterday. So we saw yesterday we have substitution for local variables, okay, which we wrote essentially as saying n for x, and then you find the x, then you return the n. Yeah. But we also have substitution. And this is what our modal substitution for global variables. Right? These are the variables that live forever. And we wrote this kind of term, m for u. And we found the u, and in this case we would just return the m. But now we're a little, well, we need to extend this operation, because what we're plugging in for m will be something that depends on some context psi. And the U will not stand as a U, it will stand as a closure. Okay? And what we're therefore doing is we're continuing to substitute. Okay, so what this is saying, continue to apply the local substitution. And the goal is essentially to ensure that whatever you plug in makes sense in its library context. Okay? So, or you could say to ensure that things remain hygienic. So it is built into the language that we don't keep it as a code. Yeah.
So sigma is sigma is a list of
So the sigma, yeah.
yeah, it's a list of substitutions, right?
A list of individual substitutions.
Okay.
So it's a simultaneous substitution.
A simultaneous, okay.
So here, sigma, right, u will be from u's type will be psi A. And sigma will be from psi to gamma. So we can apply it. And the result, right, if you plug in this m, so m is also of this type, so m is also of type A in psi delta. So this is what this means essentially. So that means we have in the end, we apply this to them, okay, we have a context switch back to gamma. So we get gamma get it back into gamma. So we moved it from, if your m used x and y, but we needed it to be in a context where we had a and b, we're going to rename it to a and b. Now here we did actually more than just renaming it. We continued to plug in our tails. Okay? We stuffed into our hole, into this vector, we continue to stuff in like tails of b as we come out of the recursion. So we do a little bit more than just renaming. Yeah?
I'm a little confused by it being called the closure because it feels like we are applying the substitution.
But we're only applying it as soon as we know what U stands for. Before, it's a suspended substitution. Before we can't do anything. But it is different from a function application. Okay, so in a sense, if you would do a function application, I'm going to go lambda x, okay, and maybe you don't know yet what this stands for. Okay, so this was our U previously, because we didn't know what it stands for, okay, and then we apply it in the second one. Now, this reader will not fire if it is under a box, right? Because we don't evaluate under the box. So it will persist. Okay. This is different from here, because as soon as you know what U stands for, the substitution is going to be applied. And we know in here, right, eventually the substitution will be applied. It will come to the fact that you will have, whatever you plug in for U, you will apply the substitution. You will have eventually, whatever you have in here, and you're going to do a Y for X. That's the substitution you're going to apply to whatever you plug in for U. Right? So this substitution must happen. And rather than saying, delaying it, here it will be delayed. Okay? Eventually you'll run the box, and then you'll apply the substitution. Here we're going to apply the substitution as we build. So the essential difference is why we want to have contextual types versus just functions is because they have operationally a different behavior. And functions are not transparent, they're black boxes, okay, they fire if you ask them to evaluate. But we don't want to evaluate under the box. Okay? We want to treat it as syntax, and we just want to splice it in syntax. And what we need to do is, we need to rename sometimes these pesky variables. Okay? But what this theory actually tells us, we can build like more interesting combinations of syntax, okay, where we actually replace like a variable b with table b, for example. But it's still just splicing it in. It's like a giant puzzle. You're like connecting them, and you make sure that all your borders are right.
If all variables were always fresh, would we need sigma still to handle the holes correctly, or would we not need sigma?
Right, so if you would have always fresh, or let's say De Bruijn indices, okay, so you have sometimes unique representation, then you can often get away with the sigma, okay, because essentially you had a unique representation, okay, so the variable, De Bruijn index 1 just makes sense, okay. But often it is still, will be still less powerful, okay, because of the fact here, okay, we're building something that is going to be head of table B, so what we're plugging in is just a variable. So, but in many cases, okay, it would be just the same. In fact, some of you might have used well-scoped De Bruijn indices for encoding terms in Comparact. Everyone's used well-scoped De Bruijn indices? One, two, couple. What is a well-scoped De Bruijn index? Okay, it's a term that has a sort of an upper bound, right? And that upper bound tells you the size of the context. That's the contextual type, okay? Because what it does, it's really, so this is a term, and then you keep also the length of this side to know that whenever you plug in a variable, it is within that bound. Okay, so it is a well-scoped De Bruijn term, and that's exactly what this is, except that this doesn't require you to work with De Bruijn indices. You can work with names, or you can choose whatever other implementation you ever like. Okay? You can use De Bruijn indices, you could use locally nameless, you could use nominals, okay, you can. This is not fixed to a particular implementation strategy. Yeah.
So I'm curious, I think this is very cool, but so my question is like more of a soft history question. When you were like working on this, like, this contextual model types, were you motivated by the problem first and you tried to develop the theory, or did you work out the beautiful theory and try where to fit this, type system?
Yeah, that's an interesting, good question. So actually what happened is that, I worked during my PhD on theorem proving. I worked on the logical framework 12, and I wanted to do proof search in 12, which is some of you might know, it's a logical framework. And one of the problems you need to solve is higher order unification and higher order logic programming. And in central, you have to have higher order unification. And in order to describe holes in terms, to then unify them, okay, I wanted to have holes. Okay, so the prevalent idea at that time was that you model holes with higher order unification problems as functions. And that meant when you were instantiating this hole, you always have to do a beta reduction. So you cannot directly reason about equality between two terms. It's equality modulo beta. And that makes proofs just annoying. Okay? And it's also not how people implemented it. Okay, so there were previously formulations that used essentially De Bruijn indices and explicit substitutions, and there people did think of these things as more like what we now call the contextual type. So that was me, okay? And we had Frank as an advisor, and there was another student, Alexander Nemetsky, who was not working on theorem proving. He was working on sort of a meta programming, but with effects. Okay? So he wanted to model holes in programs that had, for example, a state. Okay? And he wanted to sort of trap the state in which a given hole was living in. And so, so I think we, eventually sort of Frank realized we were working on the same problem. And then, we kind of generalized essentially what I already had to a more general theory, maybe this contextual type theory.
Cool, thank you.
And then after that, I think people realized, oh, it is much more general than that. Right? So then Cyrus Omar was like, okay, we can use this. He wanted to use it in sort of his programming environment Hazel, where he wanted to make sure that every edit action you do is not typed. And after that, after we had written the paper, one of the problems that was sort of open was how do you actually reason inductively about higher order syntax definitions, okay, which the logical framework is based on these higher order syntax definitions. Doesn't matter if you know what that means. But we didn't know how to reason about these inductively. And then I realized, well, actually contextual types allow us to reason about them. And so, yeah, so I think that's sort of the journey that we started, and that's when I ended up in programming languages. So, you know, and I think at that time, around 2008, 2010, what happened, sort of the programming language community was growing fond of using Coq and doing more mechanizations, and concert happened and so on, right? And so then it was a natural place for me because I had worked on these systems before, and now the programming language community, you know, was also interested in these kinds of systems. Yes.
Okay, so I know I already asked about communications, and I understand that there's been doing evaluation, but it feels like there are a lot of parallels between, would it be reasonable to think of this as like a syntactic, or, because like, this, one of the things is just like SEC, but for syntax. Kind of.
Yeah, you could maybe, so there's definitely evaluation under the hood, right?
Right,
Because
and it
under the
feels
hood,
like a
you-
contextual equivalence.
Yeah, so under the hood, you're doing a little bit of evaluation in this case.
Yeah.
So we're sort of having essentially two different forms of abstractions and two different forms of applications. And so this is an abstract. The box is an abstraction that basically allows me to go inside and eliminate these closures. In a function, functions are still first as values. I believe touch them.
So, I guess, currently my intuition, or like my mental model on this is very much leaning towards doing a lot of the things that I structured that with communication, like in abstract machine setting and applying it to these, to like the syntax here with the holes. And I want to make sure, other than the fact that obviously we're not talking about like a reproduction of compliments or something here. Given that you earlier said we should not think about boxes as continuations, I want to make sure that I'm not like.
So continuations for me are high-order functions.
Okay.
And for me, the boxes are not real functions. So that's my main distinction here.
Okay.
So, because for me, functions, right, you would build a functional closure, you don't evaluate inside, you might, with continuations, you might build a stack of these functions, okay, it can be nested inside. Yes, boxes can also be nested inside, but they will have a very different behavior.